Okay, good afternoon, students. I hope my voice is audible to you all, and also my slides are visible. I welcome you all to the first tutorial of this course, Introductory Organic Chemistry 2, which is conducted by NPTEL, whose course instructors are Professor Harinath Chakrapani and Professor Neeraja Dashaputri from IISER Pune. I'm your PMRF teaching assistant, Deepika. I'm doing my PhD in chemistry at IIT Bombay. And in today's first tutorial of this course, we are going to try to solve a few questions on the topics aromatic electrophilic substitution reaction and principles of NMR spectroscopy. So, in this week, since 21st of August, uh, a few videos were made accessible to you all by Professor Harinath Chakrapani sir. I hope you all have gone through all the video lectures provided by him. And so, on the basis of the lecture topics, we are going to try to solve the few questions in this tutorial. Okay, so it's almost 3:10 p.m. So let us just start with the first question of today's tutorial. Which of the following is rate determining step in electrophilic substitution reaction? So if we talk about the mechanism involved in electrophilic substitution reactions, what happens? First, the aromatic substrate attacks on the electrophilic reagent which is present in the environment. Okay, so first the electrophile gets generated and the attack takes place by the aromatic substrate on the electrophilic reagent. This slow attack results in the formation of the carbocation intermediate of electrophilic aromatic substitution, which is known as sigma complex. And this carbocation intermediate formed is resonance stabilized, and this resonance stabilized uranium ion is better known as sigma complex. After the formation of this sigma complex, in the subsequent step, a base present in the reaction medium deprotonates the sigma complex and results in the aromatization of the uranium ion, giving the desired product. Thus, the desired product of this electrophilic aromatic substitution is obtained in the reaction. So, the main steps involved in electrophilic aromatic substitution are addition of the electrophile making the Ce bond, where we observe the formation of sigma complex, and in the step 2, proton transfer happens, restoring the aromaticity of the uranium ion, giving the desired product. So between these two main steps, the first step is slower as compared to the proton abstraction step, And as we know, the slowest step is the rate determining step in the reaction. So in this mechanism, the first step is always known to be the rate determining step in electrophilic substitutions. So out of the four options given for the question number 1, which of the following is rate determining step? Generation of electrophile, attack on an electrophilic reagent by benzene ring, formation of product, or all of the mentioned. So we observe that option number B is the correct answer for question 1, where we saw the formation of sigma complex. Okay. Next question is again a very simple question from the theory part. Which of the following act as catalysis in the nitration of benzene? We know that in nitration reactions, we use two types of acids. So you have to memorize or figure out which acids and in what concentration we use those acids for a efficient nitration reaction. Always remember, we use concentrated H2SO4, concentrated sulfuric acid, as a catalyst in the nitration of benzene. Benzene is treated with a mixture of concentrated nitric acid and concentrated sulfuric acid at a given temperature to achieve an efficient nitration reaction. In the subsequent questions, we will also go through the mechanism of nitration reaction. Okay. So, always remember concentrated H2SO4 is used as a catalyst in nitration reaction of benzene. Next question is the product of Friedel-Crafts acylation reactions are these alkyl benzene or alkyl amine or aryl ketone or halobenzene. To figure out what product we observe in Friedel-Crafts acylation, first let us give a brief introduction of Friedel-Crafts acylation, how this happens and what kind of mechanism it follows. Okay. So, at first, like we said in electrophilic substitution, the generation of electrophile happens and that happens in presence of aluminium chloride in case of Friedel-Crafts acylation and alkylation. So for acylation, we use acyl chloride in presence of AlCl3, where you get the generation of the desired acylium intermediate, which is the desired electrophile. And in the next step, which is the first main step of substitution reaction, which is attack of the aromatic substrate to the electrophilic reagent. Okay, so this attack takes place on the electrophile, and look at the arrow how it goes, and by the arrow pushing you will get a sigma complex after this step, and after the formation of the sigma complex, like we observed in the previous question, in the subsequent step, basic moiety present in the environment will abstract a proton from the uranium ion, and after the abstraction of the proton, this bond will break and the carbocation will get neutralized, restoring the aromaticity to give you Friedel-Crafts acylation. So if you look at the product of Friedel-Crafts acylation, what is it? Is it alkyl benzene or alkyl amine or aryl ketone or halobenzene? It is a aryl ketone. In case of Friedel-Crafts alkylation, we get alkyl benzene as the product. But in case of Friedel-Crafts acylation, following this kind of mechanism, we observe the formation of aryl ketone. But in organic synthesis, If the chemists require alkyl benzene using Friedel-Crafts acylation, then they will have to do simultaneous reduction of this carbonyl group. Okay, and commonly used method for reduction of this carbonyl group is via Clemmensen reduction or Wolff-Kishner reduction. So the acylated product can be converted into various derivatives of organic compound using Clemmensen reduction or Wolff-Kishner reduction or other kinds of reactions on this aryl ketone. So the answer will be option C, aryl ketone. Okay, so let us move ahead to the question number 4. How will you convert benzene into N-propyl benzene? This is another question from the topic electrophilic aromatic substitution. So you have to convert benzene into N-propyl benzene, and you are given 4 options. Option A, Friedel-Crafts alkylation, Friedel-Crafts acylation, Friedel-Crafts alkylation followed by Clemmensen reduction, Friedel-Crafts acylation followed by Clemmensen reduction. Okay, so we simply just need the N-propyl group installed on the benzene ring. Okay, so at the first glance, you may think that we can easily achieve our goal by carrying out Friedel-Crafts alkylation. We just have to take N-propyl chloride or N-propyl bromide, and we can easily generate the electrophile using AlCl3. And after the generation of electrophile, like we observed the mechanism, we can easily convert benzene into N-propyl benzene. But in this particular example, the desired product N-propyl benzene is not observed if we carry out Friedel-Crafts alkylation. Okay, why does it happen? If we recall the mechanism, you will remember the formation of electrophile from this N-propyl chloride and AlCl3. What happens? AlCl3 will take up the chloride and the electrophile, positively charged electrophile, will be formed, which will be ready to get attacked by the aromatic substrate. But in case of N-propyl chloride, when the chlorine atom is taken up by AlCl3, at first the primary carbocation is formed. Okay, at this carbon, the primary carbocation is formed. But is it stable? No. Whenever there is a scope of hydrogen shift or alkyl shift to give a more stable carbocation in a reaction, then that pathway is always followed. Although at first you will get the primary carbocation at this center, immediately one proton from this carbon atom will get shifted, in turn neutralizing this carbon as CH3. But since you have shifted one proton from here, you will get a secondary carbocation at this center. And as we know the series, stability series, tertiary carbocations are the most stable ones, followed by the secondary, and followed by lastly the primary carbocations. Okay, primary carbocations are highly unstable and they always try to get rearranged or get neutralized via elimination reactions. So here also, when we take N-propyl chloride in case of Friedel-Crafts alkylation, the electrophile doesn't stop at primary carbocation step. It readily rearranges itself to the secondary carbocation, which gets attacked by the benzene at this center, giving you the undesired rearranged product. Okay, and in the course of the reaction, maybe very trace amount of the desired product you will observe, due to the fast attack by the benzene ring, but most of the amount in the product will be occupied by this rearranged product. Okay, and I hope you understood how you get this rearranged product in case of Friedel-Crafts alkylation if you carry out the reaction with N-propyl chloride. So if we think of Friedel-Crafts alkylation, we will not get our desired product. Okay, and even if you get, it will not be beneficial because it will be very less amount of the product in the mixture. So if you get an efficient synthesis of N-propyl benzene via benzene, you will have to follow another route, which is Friedel-Crafts acylation followed by Clemmensen reduction of ketone. So if you carry out Friedel-Crafts acylation, okay, suppose we are carrying out only option B, what will happen that in that case you will get a ketone group also. Okay, a ketone functionality you will get aryl ketone you will observe, so you will not get N-propyl benzene. What you will have to do is, you will have to do first Friedel-Crafts acylation, and then you will have to reduce the CO group. Okay, like you can think of using CH3, CH2, COCl. Okay, suppose we are using CH3, CH2, COCl having 3 carbon, and that acid chloride can give you the desired aryl ketone as CO here and ET here. And if you reduce the CO carbonyl functionality in the COET group, you will observe the desired product, which is N-propyl benzene. Okay, like from acylation you will get a carbonyl group here, and after reduction you will get a propyl group attached to the benzene ring. Okay, so the correct option for the conversion of benzene into N-propyl benzene will be Friedel-Crafts acylation followed by Clemmensen reduction. So the correct answer will be D for the question. So next we have a reaction which is given as dichlorobenzene is given, and you have to treat it with concentrated nitric acid and concentrated sulfuric acid. So what is the reaction condition given? As you all know, it is a nitration reaction condition. Okay, so we are throwing the dichlorobenzene for nitration reaction condition, and what will be the major product formed in the reaction you have to identify. You are given these 4 options. 2 of the options are giving you the nitrated dichlorobenzene, and 2 of them are giving you sulfonation. Okay, you can straight away cancel option B and D, as in sulfonation we use only concentrated H2SO4. Okay, only concentrated sulfuric acid is used for sulfonation, and when you use concentrated nitric acid in presence of concentrated sulfuric acid as catalyst, you get nitration. Okay, so either option A will be correct or option C will be correct. So now it will depend on the directing effect of these 2 chlorine atoms. They will direct the incoming nitroelectrophile to their ortho position or meta position or para position. Let us go through the mechanism involved in the reaction. Okay, so here a few basic points of electrophilic ring substitution reactions have been mentioned. You may go through these points, but we have already discussed most of them. We will just discuss the nitration points. Okay, so nitric acid and sulfuric acid is used to generate the nitronium ion as electrophiles. So here the nitrating agent is this nitronium ion, okay? And what happens, like all the electrophilic substitution aromatic reactions, the benzene ring will attack on this nitronium electrophile to give the sigma complex. And as we all know, this resonance stabilized sigma complex will then undergo deprotonation to restore the aromaticity and gives you nitrated benzene. In first step, production of electrophile takes place from H2SO4 and nitric acid, and this balanced chemical equation shows the formation of the desired nitronium electrophile in the reaction. Okay, and the aromatic ring attacks on this nitronium electrophile depending upon the ortho para meta directing effect of the substituents present in the benzene substrate. So here in the aromatic substrate we have two chlorine substituents, okay, and chlorines are ortho para directing substituents. This resonance stabilize these resonating structures are showing how in this dichlorobenzene the ortho and para positions, like suppose for this chlorine atom this one is the ortho and this one is the para, and for second chlorine atom this one and this one, these two are ortho and this one is para. You can see how the ortho and para positions are electron rich in these resonating structures. Okay, so if you have to attack on the positively charged nitronium electrophile, the attack will take place definitely from the electron rich positions. This is why when the dichlorobenzene is treated with the generated electrophile, the attack leads to the attachment of the nitro group at either the ortho positions or at the para positions. Okay, so if you look at these resonating structures, you will get 4 types of products, out of which 2 and 2 will be identical. Okay, so these two products can be formed by the reaction of 1,3-dichlorobenzene in the nitration conditions. 2,4-dichloro-1-nitrobenzene and 1,3-dichloro-2-nitrobenzene. Okay, so these two products are possible by looking at the orthopara directing effect. So if we go to the options now, but we had 1 nitro and 2 nitro. Okay, so if we go to the options here, this product will be formed due to the orthopara directing effect of the chlorine atoms. Okay, the meta substituted product will not get formed in the nitration of 1,3-dichlorobenzene. So option A will be the correct answer. I hope this is clear. With this, now we are moving to the questions of the principles of 1H and 13C NMR spectroscopy. So the theory part has been taught in the video lectures taken by Professor Harinath Chakrapani in the first week of the course. So we are going to discuss a few basic questions on 1H and 13C NMR spectroscopy, by which we will try to brush up the theory part of the NMR spectrum. So first question we have from the NMR spectroscopy part is the number of signals expected for the given compound This bicyclic compound is given to you and you are asked the number of signals expected for the given compound in both 1H and 13C NMR spectra. Okay, so you must know that in 1H and 13C spectroscopy, the protons which are in different chemical and electronic environments will lead to different signals. Similarly, in 13C spectroscopy as well, carbon atoms which are in different electronic environments will lead to the different signals in 13C spectrum. Okay. In case of symmetric molecules, if you find that two carbon atoms are in the same electronic and chemical environment and they are completely symmetric in the molecule in terms of their positions, they will give only one signal in 1H and 13C. Okay, if it is carbon, it will give only one signal in 13C, and if it is proton also, if in the symmetric structure uh, of an organic molecule, two protons are oriented in such a way that the molecule is completely symmetric and they are facing the exact same electronic environment in the structure, they will lead to only one signal in the 1H spectrum. Okay, so keeping this fact in mind, let us try to figure out how many numbers of signals you will observe in this compound for 1H and 13C. Let us first try to analyze the 1H spectrum signals. Let us count the number of different types of protons. By different types of protons, what I mean? The protons which are in completely different electronic environment. Okay. So let us start with this positions protons. Okay. So this is an sp3 carbon having two protons, one at axial and one at equatorial position. Okay, so these two will be in an exact same electronic environment. Okay, not only these two, if you look at the structure, you can cut this molecule into exact two similar halves by passing a plane via this atom, which will pass through this center of this molecule. Okay, which will cut the molecule into two equal halves through this axis. I hope you can visualize. Okay, this axis via this plane passing through this atom can cut the molecule into two equal halves. Thus, this molecule will be symmetric in terms of that plane. Okay, so due to this sigma symmetry present in the molecule, these two carbon atoms and these two carbon atoms, they will be similar to each other. I hope you are getting to know this carbon and this carbon will be identical chemically and electronically as well. This carbon and this carbon will be identical and this carbon and this carbon will be identical. Okay, so when it comes to the protons present in these two positions, they are interchangeable between axial and equatorial positions. This is why these four protons will give only one signal collectively. Okay, these two sets, why these two sets will give one signal, I hope that is already clear. This is due to symmetry. But why individually these two protons present in the same atom will give one signal? This is due to the interchangeable behavior between axial and equatorial positions. So these sp3 hybridized carbon proton atoms will lead to only one signal in 1H spectrum. Okay. Then we have these two protons. Okay. In the structure, two protons will lie in the downward face in these two carbon atoms, and due to symmetry both these protons will be also identical in terms of chemical and electronic environment. So these two protons will also lead to another signal in the 1H spectrum. So thus till now we have obtained two signals in the 1H spectrum. Okay. Now let us come to the protons present in these two carbon atoms. So we have four protons in these two carbon atoms. Okay, one are axial for both carbons and two are equatorial for both. And due to symmetry, whatever these two protons will give signals, similar signals will be given by these two protons also. But these axial and equatorial positional protons will not be this time interchangeable. Why is it so? Because both, like the axial and the equatorial position proton, are in different chemical environment this time. These are lying near this chlorine atom in the structure, and the molecule is oriented in such a way that the chemical environment of these two protons are now affected by this chlorine atom present. This proton is lying near to this chlorine atom present in the bridgehead position, due to which this proton, which is in the same face of the chlorine atoms, will be affected by their presence. And these two protons will now be in different chemical environments. Their electron densities around the protons will also be different due to the presence of the chlorine atom now. Okay, due to the molecular orientation, this is why the two protons, axial and equatorial, the two protons will give two different signals. And in the similar way, this carbon is also symmetric as this one. So both the protons present in this carbon also, this fourth one, whatever is labeled as fourth one, it is actually in the above face, in the same face of this bridgehead ring. So this one will also be affected by the presence of this chlorine atom, and this is why these two protons will also give two distinct signals. Okay. Now the last carbon atom is left. This carbon atom is also possessing two protons, and in the molecular orientation, these two protons will also get affected by the presence of the chlorine atoms. Okay, these two are in chemically distinct environment, and they will lead to the formation of two distinct signals in the 1H spectrum. Okay, at the first glance, if you look at the structure and if you do not consider the chemical environment of the protons, completely ignoring the molecular orientation, You may think that, oh, this will simply give 1, 2 and 3 signals in the 1H. But this is not true. In this uncommon example, you will observe total number of 6 signals in 1H spectrum. Okay, so the protons present in these two carbon atoms are chemically distinct due to getting affected by this chlorine atom. Okay, thus it leads to the formation of 1, 2, 3, 4, 5 and 6. 6 different types of signals in 1H spectrum you will observe for this molecule. Now let us count the number of signals for 13C. Okay, so in case of 13C, let us count the number of different types of carbon atoms present. So the numbering has started from this carbon. Okay, this is first, and due to symmetry 1 and 5 will be same. Okay, 1 and 5 are exactly in the same electronic and chemical environment, so they will lead to the formation of only one signal. Okay, 1 and 5 will give one signal. Then 7 and 6 we have. 7 and 6 will also give the only one signal due to symmetry. So we have two signals till now. Okay, this one and this one. And then similarly 2 and 4 will also give same signal. So 1, 2, 3, 4 and 5. We have 5 different types of carbon atoms in the molecule present. And these 5 different types of carbon atom will lead to the formation of 5 different signals in the C13 spectra. I guess the 13C analysis was not that tough, but due to the molecular orientation of the structure, the 1H spectrum is actually observed to be very uncommon. Okay, so you have to remember, for these kinds of particular examples, chemical environment for the protons matter a lot, which lead to different signals in case of the diastereotopic protons. Okay, so thus the correct option for the question, the number of signals expected for the given compound, will be 6 and 5. Okay, the diastereotopic protons gave us different signals, whereas the anisotropic protons gave us only one kind of signal. Okay, thus 6 signals in 1H and 5 signals in 13C spectrum. Then we have the next question from the topic principles of NMR spectroscopy. Methyl 4-oxopentanoate exhibited signals delta 208, 172, 51, 37, 32 and 27 ppm in its 13C NMR spectrum. The signals due to the methoxy C1, C4 and C5 carbons are. So you have been given the marks here. Okay, the carbon numbering are here, and you were asked what will be the chemical shift values for the labeled carbon atoms. Methoxy, this methoxy carbon atom 51, the C1 which is this ester carbonyl, C4 which is this ketone group, and C5 which is this methyl attached to the ketone carbonyl. You have been asked about the chemical shift values for these carbon atoms. Okay, for that you will have to memorize the values of the approximate chemical shift of different types of carbon atoms. So the chemical shift values mainly depend on the electronic environment and electron charge density around the carbon atom present in the molecule, and depending on the electronic environment, different types of signals are observed in C13 spectrum. So in the methoxy, you will see a carbon atom which is attached to an electronegative atom which is oxygen, and when these kind of carbon atoms are present in the organic molecule, OR, OCH3, like OCH2, OCH3, OR, whenever you observe OR groups in carbon atoms, the carbon attached to the O group will always lie in the region of 50 to 80 ppm. Okay. In case of CN, the values are a little less, but due to higher electronegativity, in case of CO, you will observe this value which will lie mostly from 50 to 80. Okay. So out of the options given for OME, you can see two of them are coming as 51. Okay. So definitely either option 2 or option 4 will be correct. You already know now. Then we will move to C1 carbon. Okay, C1 carbon is this ester carbonyl carbon. So for carbonyl compounds, the CO carbon appears from the region 160 to 220. Depends upon the functionality present. Okay, if the compound is an amide, then the carbonyl carbon will appear at 165 to 175, and if it is an ester, it will appear around 170. Okay, for the for acids you can observe a higher value in C13, and maximum value will go for ketone as 205 to 220. Okay, so as we can see here, the C1 carbon is actually an ester. Okay, so what I said, ester values lie near 170. Okay, so let us go to the options again. We had option 2 and 4. Okay, so between option 2 and 4, which one is giving us a value of 170 for C1? Definitely option 4. Okay, so C1 ester is 172. So by just looking at two values of carbon atoms, you can quickly tell that option 4 is the correct answer. Let us match C4 and C5 as well. So for C4, this ketone group is here, right? For ketones, what I said, the value is maximum, which lies from 205 to 220. So here also the value is given as 208. So it is in line. Okay. And for C5, which is a COCH3, the COCH3 values are not much downfilled. Okay, and they lie around the value of 25 to 40. Okay, so as here you can see, COCH3, the value is given 32. So definitely the option 4 is the correct answer here. So methyl 4-oxopentanoate exhibited these signals, and out from these signals, by observing only at 2,3-C13 NMR, we identified that this is the structure of methyl 4-oxopentanoate, and option 4 chemical shift values are in line. Okay. Once you figure out how the electronic environment of the carbon atoms are affecting their chemical shift values, and after understanding, when you remember the values, then structure elucidation becomes very easy using NMR spectroscopy. Okay. So after this, let us move to question number 9. Okay, so this is a similar question as question number 7, which we have already solved. In the broadband decoupled 13C NMR spectrum, the number of signals appearing for the bicyclooctane A to C respectively are. You are given 3 bicyclooctane molecule structures. In all of them, you have to figure out how many number of signals you will observe for each of them in 13C NMR spectrum. Let us again approach the question like we did in case of question number 7, where we counted the different number of different carbon atoms present in the structure. So this is the first bicyclooctane given to you. Okay, so in this one you can see that this molecule is symmetric. Okay, highly symmetric. You can cut this molecule into 2 equal halves by either this plane or this plane. Okay, even these 2 planes will also divide it into 2 equal halves. Okay, so if we consider this plane of symmetry in the molecule and count the different types of carbon atoms present, you will see that this molecule contains 3 different types of carbon atoms. Okay, so this carbon and this carbon, these two are symmetric to each other, identical to each other, and these two will lead to one signal. And then these 2 carbon atom and these 2 carbon atom, these all 4 carbon atoms are symmetric to each other. They are in the exact same chemical and electronic environment. So these 4 are going to give you only one signal. Similarly, these 2 tertiary carbon atoms will also lead to only one signal in the 13C spectrum. Thus, you will observe only 3 signals for this compound in the 13C. For the second structure given, if you see, this is also a very highly symmetric molecule. Okay. If you see this fragment, and this upper fragment, all these 3 fragments are exactly identical to each other. Okay, so this highly symmetric molecule contains only 2 different types of carbon atoms which will be chemically distinct. Okay, one of them is this secondary carbon and the other is this tertiary carbon. Okay, these all 6 carbon atoms are exactly identical to each other in terms of electronic environment and chemical environment. Okay, these 6 carbons will lead to only one signal in the 13C spectrum. And when it comes to these 2 tertiary carbons, these 2 will also lead to only one signal collectively. So overall, this structure number B will give you only 2 signals in the 13C spectrum. Then comes the third structure of this bicyclic compound. Let us count the different types of carbon atoms present. Okay, 1, 2, 3, 4 and 5. Okay. This structure is somewhat similar to what we have already solved in the question number 7. So this is similar way. You will see that these two carbon atoms are same, these two carbon atoms are same, these two carbon atoms are same. Okay, you cannot say that 1 and 5 are also same. No, 1 is subsequent to 2 tertiary carbons, whereas 5 is subsequent to 2 secondary carbons. So 1 and 5 cannot be exactly same. But definitely it is a symmetric molecule. You can pass a plane through 1 and 5, which will cut the molecule into 2 equal halves and lead to the presence of 5 different types of carbon atoms in this molecule. So you will get 5 signals in the C13 spectrum for the compound. Okay. As we saw that in the broadband decoupled C13 spectrum, the number of signals appearing for A to C will be 3, 2 and 5 respectively. Okay, so option 2 will be the correct answer for this question. Next question, this is also similar to the question number 8 which we solved, okay? But this one is actually 1H NMR spectroscopy. But similarly, if you know and understand how the chemical shift values appear for different protons and carbons, you can easily tell how the structure should be elucidated. Okay, so let us try to solve this question. Which of the following compound has the 1H NMR spectrum? 2.4 singlet 3 hydrogens, 3.9 singlet 3 hydrogens, 7.25 doublet 2 hydrogens with a coupling value 7 Hz, and 7.95 doublet 2 hydrogens with a coupling value 7 Hz. Okay, so in the options you are given 4 aromatic compounds. Okay, and if you look at the 2 last chemical shift values given, all of them will give 2 such signals. Okay, so looking at the aromatic region values, we cannot tell which structure the question is talking about. So we will have to analyze the structure by looking at the other 2 chemical shift values given. Okay, so apart from these aromatic region protons, what do we have? We have OMe protons in the option 1. We have OMe and methyl protons in option 3. In option 2, we have COCH3 and OMe protons. And in option 4, we have methyl and COCH3. Okay. If you recall the chemical shift values for 1H spectroscopy, you will find the variation as when it comes to OMe protons, the values always lie mostly from 3.5 and above. Okay, the OMe proton values always lie above 3.5. Okay, mostly even more than 4. And when it comes to COCH3 protons, these values will be observed in case of mostly around 2.5. Okay, so and in case of these methyl substituents attached to an aromatic ring, the values lie from 2.3 to 2.7. Okay. So now let us go back to the question. We have been given 2.4 singlet 3 hydrogen and 3.9 singlet 3 hydrogen. So if we have a 2.4 value, we, by matching to this correlation chart, we will know that one methyl substituent is present in the aromatic ring. Okay, so either option 3 will be correct or option 4 will be correct. Then we will look at the value 3.9, which is singlet 3 hydrogen. So for the 3.9 value, you must know that it is matching with, with the value observed for OMe protons. Okay. As we went through the correlation chart, we observed the OMe value always lies above 3.5. Okay. So here the values are matching with one proton which is corresponding to a methyl group attached to the aromatic ring, and the second one is the OMe protons. Okay. So out of these two structures, 3 and 4, we have come to the conclusion that the correct answer will be option 3. And in this structure, the values have also been correlated. Like we said, the methyl group attached to the aromatic ring is giving you a value of 2.48, which will be a singlet. Okay. And the COOMe protons are giving you a value of 3.98, which will also be a singlet. Then the aromatic region protons are doublets, which will be value of 7.958 and 7.258. So now if we talk about the differences in these two values, why this value is less? This is due to the presence of this electron donating group in the ortho position of this proton. Okay. Due to the electron donation from this methyl group, the electron density around this proton will be higher. This is why the chemical shift value will be more upfilled for this proton as compared to this one, because this one contains an electron withdrawing group in the ortho position of it. So the electron density will be abstracted away from this proton, and this is why this value will be downfilled. Okay. That is why this value is more downfilled than this HC proton. Okay. So thus electron withdrawing group and electron donating group present in the structure also affects the chemical shift values. Thus we observe that the correct structure for the given 1H NMR spectrum data is option number 3. So next we have another question from 1H spectrum, which will be a little difficult maybe as compared to the previous questions. An organic compound Q exhibited the following spectral data. You have been given 1H NMR 7.2, 1 hydrogen doublet, 5.1, 1 hydrogen multiplet, 2.1, 3 hydrogen singlet, and 1.83 hydrogen doublet. And for the carbonyl carbon, you have been given that it gives one signal for carbonyl carbon at 170 ppm. So what kind of carbonyl carbons give signals around 117 13C? It has to be either ester or acid or amide. More accurately, it must be an ester. So in the options given, what kind of carbonyl compounds do we observe? We have ester here. 3 options are containing ester and 1 is containing ketone. But ketone value was found to be 205 to 220. So this cannot be a ketone, okay? We will straight away cancel the option 3. Now we will have to look at the 1H NMR values to find out among all these 3 options which option is the correct one. So we have been given one signal at 1.8 3 hydrogen doublet. If we look at this fourth structure, this fourth structure is containing 2 OMe groups. Okay, so accordingly it must give 2 signals which will lie from 3.5 to 4.9. So are these data containing 2 such signals? No, right? We are not observing 2 signals for 2 OMe groups. So option number 4 we will also get cancelled from this questions. Okay, so we are left with option number 1 and option number 2. Are these two containing a proton lying near the 1.8 region? Yes, it is containing one methyl on it, which will lead to a value of 1.8. Okay, and since it is attached to this double bond, like we saw in case of aromatic methyl substituents, they were coming in 2.5 region. Okay, so here also, as it is attached to an olefin, this value will come at 1.8. So definitely option 1 and 2. Out of these two, one option will be correct for the question. So now these two structures are actually very similar. The difference comes from only the cis and trans stereochemistry of this double bond. And for identifying the structure given in the data, that it will be the cis one or trans one, we have to know the coupling constant of protons. And not much have been covered on the coupling constant in this week's lecture, as I know. So I have included some introductory values in this question. So what happens when we have a double bond in the organic molecule? If you have such kind of vicinal protons which are lying in a cis fashion, these two protons will give you a signal having a J value ranging from 6 to 14. Okay, like here you have been given J values, right? In this one you have been given J value, and if the protons are vicinal cis, the J value lies from 6 to 14. If the protons are vicinal trans, the values lie from 11 to 18. And these two values are typically 10 and 16. Okay. And then the geminal protons also couple to each other, and geminal protons coupling leads to a J value of 0 to 3 and typically 2. Okay. So these 3 kinds of coupling are very important in organic molecules, and As you can see, in case of vicinal cis, you are observing a value of typical 10, and in case of trans, you are observing a value of 16. So in the question, you are given a value of 16 Hz. Okay, so this 16 Hz proton is basically talking about this proton, the proton attached to this carbon atom, and as the J value is lying in the region of vicinal trans, so the structure will be containing a trans vicinal proton atoms. Okay, so out of this 1 and 2 structures, structure 1 is found to be the correct one. Okay, if structure 2 had to be correct, the J value must be around 10. Okay, so thus you saw that the E and Z stereochemistry of double bonds are also dictating the 1H NMR chemical shift values of the organic compounds. And due to these vicinal trans coupling, we are getting a signal of 7.2 for the proton at this carbon, giving a doublet, and between the doublet, if you calculate like the doublet peaks, you have two peaks there, right, in the signal, and the two peaks will be apart from each other by a value of 16 Hz. So the correct option was option 1 for this question. Okay. So thus we have found out the correct structure for the data. Let us move to the next question now. This is very similar to what we have already solved, but just it is a little higher level because it is containing both 1H and 13C spectral data. And with the help of whatever we have gone through till now, whatever questions, I hope this question will be very easy for you all to solve. The structure of the compound which displays the following spectral data is. So you have been given given the IR data also, but to solve this question, as in the week 1 only NMR spectroscopy has been covered, we will take the help of only 1H spectral data and 13C spectral data for this question. Okay, so if we look at let us go for the 13C NMR spectrum first. So you are given 197, 165, 130, 129, 114, 56 and 26. And if you look at the carbonyl carbons present in all the 4 options, you will see ester, ketone, ketone and ester again. Okay, so the value is 197, way more than 170, which is a typical value of an ester. Okay, so looking at the value 197, you can cancel out the options which are containing ester functionality. So we will straight away cancel out option 1 and option 2. Okay, we are left with option 3 and 4, which are containing ketones. And now you have to figure out which structure between these 2, 3 and 4 is correct. Again, here the values I have included, but if you analyze these two options, okay, the two ketone options, whatever we are left with, let us now go through the proton NMR spectrum. Okay, it is showing a 2.8 singlet 3 hydrogen, 3.8 singlet 3 hydrogen, 6.9 doublet 8 Hz to hydrogen and 7.8 doublet 8 Hz to hydrogen. So 2.8 singlet 3 hydrogen is corresponding to either COCH3 group or 1 methyl attached to the aromatic aromatic ring. But here you have COCH. So yes, it is lying with the option 3 and 4. Next you have 3,8 singlet 3 hydrogen. 3,8 is corresponding to 1 OMe proton. Okay, so both of these are containing 1 OMe each. Then you will have to see that two more signals are given in the 1H spectrum. If we consider the third option, in the aromatic region, how many proton signals will you observe? 1 and 2. Because the molecule is symmetric and these two are identical and these two are identical. So 1, 2. Two signals you will observe in the aromatic region. But for the fourth option, you will observe 3 different types of proton signals in the aromatic region. Because this molecule is not really symmetric and these all, sorry, not even 3, it will give you 4 different kinds of proton signals. Okay, but in the option you are given only 2 types of protons in the aromatic region. So out of option 3 and 4, you can choose the option 3 as the correct answer. Okay, option 3, which is this structure, the symmetric molecule, which will lead to the formation of only 4 signals in the NMR spectrum. Next, let us move to the next question. The number of 1H NMR signals observed for the following compound is. We have already solved such kind of question which depends on the topicity of the protons present in the structure. Okay, you will see that homotopic and enantiotopic protons lead to the formation of only one type of signal in the spectrum, but when it comes to diastereotopic protons, they give different distinct signals. So is this molecule symmetric? If you visualize the orientation of this ring attached to the phenyl ring, yes, this structure is symmetric, okay? And being the molecule symmetric, these two types of protons will be enantiotopic. This is why these two types of protons will lead to only one type of signal. Okay, so in this symmetric molecule, you will observe 1, 2, 3, 4 and 5 different types of proton signals in the 1H spectrum. Okay, so you can see that these two protons are also identical due to the symmetry, and these two are also identical due to symmetry, and thus the number of protons observed in the compound will be 5. So thus we have arrived at the last question from the topic principles of NMR spectroscopy. Okay, so let us quickly revise what questions did we discuss in today's tutorial, which was based on the topics aromatic electrophilic substitution and principles of NMR spectroscopy. First we discussed the mechanism of the common electrophilic substitution reaction, and we saw that between the two main steps involved in the substitution reaction, the first step, which is addition of the electrophile to the benzene ring, is the slowest step, and the product formed in the step is called sigma complex. And this is why we decided that the slowest step is the rate determining step for the aromatic substitution reaction. Then we discussed how concentrated H2SO4 is used as a catalyst when it comes to nitration of benzene. We also discussed the mechanism involved in Friedel-Crafts acylation, and we saw how we get aryl ketones as the products in case of Friedel-Crafts acylation reactions. Then we talked how we can convert benzene into N-propyl benzene, where we observe the rearrangement of the electrophile generated in the very first step into a more stable carbocation, which led to the formation of rearranged product if we involved Friedel-Crafts alkylation. That is why we had to carry out the conversion by using Friedel-Crafts acylation followed by Clemmensen reduction. After that, we discussed about the orthopara directing effect of the chlorine atoms by looking at the resonating structures, and we observed which positions in the dichlorobenzene were electron rich, which would attack the nitronium ion, and we saw that option A was the correct answer. In the next question, we figured out how many different number of signals were observed for the compound in 1H and 13C NMR spectra, and in this exceptional example, the distereotopic protons were leading to distinct signals in 1H NMR spectroscopy, whereas in case of anisotropic protons, we observed only one signals for multiple protons. Then in question number 8, we tried to figure out the spectral data for the given structure of 4-oxopentanoate, and we matched the OME values and C1 values first to the carbon spectrum data, and we saw that the option 4 was the correct answer. In question 9, we again tried to count the number of distinct carbon atoms and tried to figure out how many number of signals were observed in the 13C spectrum of the compounds A to C. And in question 10, we took help of 1H NMR to figure out the structure of one organic compound, and by matching the values, we observed that the correct option was option number 3. Here we also talk the aromatic protons being upfilled and downfilled when they are present ortho to electron donating and electron withdrawing groups. Okay. And then in question number 11, we tried to figure out the structure of one organic compound Q based on the 1H NMR spectroscopy and 13C carbonyl signal. Here we talked about vicinal cis and vicinal trans coupling of alkenes and saw that the correct structure of the compound was option number 1. Again, in the next question, we took help of both 1H NMR and 13C NMR and tried to solve the structure of an organic compound, and we observed that option number 3 was the correct answer, which contained two types of aromatic protons. And lastly, we again tried to figure out how many 1H NMR signals would be observed for this given compound. Okay, so with this we have come to the end of this first tutorial of the course. I hope everything was clear to you. You can ask any question or queries if you have. Thank you all for joining for today's first tutorial. And again, in the subsequent weeks, we will be meeting for the course Introductory Organic Chemistry 2, and we will be solving more questions on the weekly topics. But I would suggest you to go through the video lectures first so that we can easily understand the questions in the subsequent tutorials. Thank you.
Thank you.
Ma'am, answer for the assignments, ma'am.
Yes,
Assignments, ma'am. There we have stereochemistry, na?
uh, stereochemistry assignment for which course are you talking about?
Same introduction, the same topic, ma'am. In assignments, first assignment given, na?
Okay,
There we have different aromatic compounds. How to solve those compounds, we don't know, ma'am.
okay. Actually, in our tutorials, we are trying to solve some other questions from the topic. So, if you have any doubt from the assignment, uh, in the next tutorial, I will go through the assignment and I will try to give you the glimpse in the first 5 to 10 minutes of the next tutorial on the assignment. Okay?
Ma'am, thank you.
Okay.